Okay, guys, so this is video 5.5, I believe, where we're going to finish up the practice sheet. So we're going to do problems 3 and 4. So just wait a little bit. Okay, so problem 3 reads: a worker pushes a 7 kilogram shipping box along a roller track. It says assume friction is small enough to be ignored because of the rollers, and the worker pushes at 25 newtons directed down and to the right at an angle of 20 degrees. So if we're reading through the problem, I'm going to highlight again things that I think are important. So 7 kilograms, that's going to be important, 25 newtons and 20 degrees, and it's going down and right. So that's good. Also, it assumes friction is small enough to be ignored. So that means we don't have friction in this problem. So again, our first step in all of these problems is to solve for, when solving these problems is to draw a free body diagram. So a free body diagram is going to be the forces acting on our object that we care about, which is our box. So let me just draw a box here real quick because that's easy enough to do. So if this is the box, and we think about the things pushing or pulling on the box, the first thing I think about is this person. So the person is pushing down and to the right, and it's at 20 degrees. So straight down would be 90 degrees. Horizontally across is 0. So it's closer to 0. So maybe like that. And this is just a sketch to get a feel for it. And I'm going to label that the force of the person. So I'm just going to say P for person. Okay. And again, that's kind of at this angle here, which is 20 degrees. Okay. So so this is my angle of 20 degrees here. Draw a horizontal line. All right, so that angle there is 20 degrees. The only other thing I think of that's acting on this is the weight of the box or the force of gravity. So there's a force of gravity, so I'm going to draw that in, and I'll change color here. So I'll just do it. So the force of gravity I'll draw in green, and that is going, gravity always tries to pull straight down towards the bottom of the page. And I'm just going to write G for gravity like we have capital G, and that's our symbols. So we have gravity going down and the force of the person pushing down. And if we think about this box is accelerating or moving to the right. So it changes if it's at rest to start, it's going to start moving to the right when this person's pushing on it. So if it's not accelerating up or down, that means there has to be another force pushing up. And that is going to be the normal force. So I'm going to draw that arrow going up, say in blue here. And for the normal force, I'm going to label that capital N. Okay, so that sort of makes sense. And those are the forces. We don't have to worry about friction because it says that it's on rollers, so we're going to say the friction 0. So we're done with step A, or first part here, drawing our free body diagram for our block. So the next thing is the table. So I already have a table set up here. And I'm going to list the forces. So you get all the forces that are in your table from your picture. So I'm just going to write FP for the push from the person, G for the force of gravity, N for the normal force. And that's all my forces. That's all 3 that I have, the 3 arrows. That's where they come from. And then the net force, which is going to be the last thing here. So my net force is what I'm going to try to solve for, so I can solve for my net acceleration. Before I go any further, I'm going to take kind of each one of these arrows and assign them either positive or negative values, depending on whether they go right, left, up, or down. So for the first one, the pushing force, and I'm going to write that in our box. The pushing force is going down and to the right. That's what it says here. So down is the Y direction, and down is negative. So I'm going to put a negative sign there. And then right is the X direction, and that would be positive. So that's positive. Okay. Gravity is the green arrow. That only goes in a downward direction. So the X is 0 and the Y is negative. For the normal force, that is only in the Y direction because it goes up. So this would be 0 and positive. And we said that the box does not accelerate up or down. So it's balanced going up or down. So when something's balanced, we get a 0 when we add these up. So when we add all the Y directions up, we're going to get 0. Okay. For the net, it looks like the net force is equal to whatever this pushing force in the X is going to be. So so we filled in the positives, negatives, and zeros in the boxes. That is just as important as doing any of the numbers. So now we're going to do the numbers. So the ones that are in 2 dimensions, we're going to have to use some trig. So that's going to be, we've basically done one here where it says make an X and Y chart, and we labeled plus or minus. Now we're going to try to fill it in. So we're going to calculate the X and Y components for the forces and put in the table. So the X and Y components, we're going to fill this in X and Y with the sine and cosine part. So let me type, and it's going to be the force of the person in the X direction first. And that would be the size of the force, which is 25, cosine of the angle, which is 20 degrees. Similarly, for the Y, the only thing that changes for the Y here is that it's going to be 25 sine of 20 instead of cosine. And I'm going to put those in my Desmos calculator here, which we have. So it's going to be 25 cosine of 20. Again, your calculator might be a little bit different in the order in which you have to type it in, but that's how this one works. So it's 23.49. I'm just going to round that to 23.5 for the X. And for the Y, we'll do the same thing. We'll just change out cosine for sine to get the Y. And that one's 8.55. I'll just say it's 8.6. All right. So that's 8.6. All right. So we already have the plus and minus there. So I just have to put the numbers in. So we'll write them in. So this is 3.5. And this one is 8.6. So we're in pretty good shape. We got the first, or the person's force. For gravity, we're going to use the gravity equation. So big G, let me type it because it makes more sense to do that. So shrink this a little bit. So big G is equal to mg, which would be the mass of the object, which is 7, and then 9.8, which is the acceleration due to gravity. That's the little g constant. So if we put that in the calculator, it'd be 7 times 9, 8. And that's 68.6. So we're going to take that, put that in the chart here. So 68.6. Okay. So and I'll type that here to make sure that we don't forget it. Okay. All these things are newtons. I'm just kind of ignoring the units right now. So now we need to fill in the rest of the blocks. We only have the boxes that I'm highlighting now left. So if we look at the ones that are empty, so this box for the net force and the X is empty. This box here for the normal force, which is only in the Y direction, that is also empty. So we're going to solve for both of those. And the way that we solve, we just do algebra. So it's basically just adding the columns. So if I take a look at this column and I'm trying to add going down, it's 23.5 in the positive direction plus 0 plus 0. That's going to be 23.5. So it's a positive 23.5. Newtons. That is how much the net force is acting on this, because there is no Y direction. So it's only going to the right. The overall force is kind of just going to the right, and it's however big that is. For the Y direction, we need to figure out what the normal force is. So we're going to solve for this. So essentially we have this green arrow for gravity going down. And if I draw this in, there's some amount of the push going down. So those two downward forces, these two downward forces are being canceled out by this upward force and the normal force. So if I add these together, I go back to the calculator, it would be 68.6. And then it was plus, what did we say, it was 8.6, because that was our Y component here. And that's 77.2. So if I come back here, this number here is 77.2 going up. So if this is these two going down is 77.2, in order to keep it balanced and make it get to 0, it's just the opposite. So these two add up to negative 77.2. If I add 77.2, that's positive to it, I'll get 0. So 77.2 newtons going upward, that is the normal force. So that's, we solved for step 3. The last part here is to calculate the acceleration of the block. So to get the acceleration, you're going to use Newton's second law. So F net equals MA, not MS, MA. Shrink this a little bit. And we know most of the information here. So the net force is 23.5. The mass we said was 7, and we're looking for A. So we're going to divide 23.5 divided by 7 to get A. So let me go ahead and go back to Desmos and do that. So 23.5 divided by 7. And that's 3.36. So that is my answer. 3.36 would be meters per second squared. And it's going in the positive X direction because it is only going to the right. It's not going up or down. That's why we got 0. So let me do that to make it all fit. So so that is problem number 3. So hopefully that made sense. Lots of times in these problems, you get 0 for the Y and you get just one number for the X. Remember, unless you have two-dimensional kind of motion, you're not going to have to do the ending part. And on the tests, I generally make them simpler. So unless you see something that's going at an angle, a lot of times it'll be a number and a 0 or a 0 and a number, just like it was for gravity or normal force. Okay, so let's try to get to the last one here. So the last one is another picture where it has a person pulling on a rope on like a sled with some, looks like children on it. And the mass of the sled and the occupants is 100 newtons. The tension in the cord is 120. It's at an angle of 25 degrees. There's friction in this one. So there's a lot of stuff going on. And we're going to go through this basic same procedure. So we're going to draw a free body diagram first. For a free body diagram, you can just draw a dot. It doesn't have to be anything special. And then you're going to draw the arrows. So if we draw the arrows, I would say there's a pulling force, or it calls it the tension. So I'm just going to write T for tension. And that's there. There's gravity acting. So gravity is going to act downward. I don't know if I have these all to scale exactly right now, but that's okay. It says friction's going. So if I'm pulling right and up, the friction's just going to go parallel to the surface, which is going to be to the left. It's going like that. And then there's a normal force going up. Notice in this one, the normal force is not the same size as the gravity force. I didn't label normal force and friction. The normal force is less than the gravity force because the tension force is already pulling up. So the tension force has like an X component and a Y component. If the tension, if the normal force was equal to gravity, then this sled would fly off the surface, and that's not what's happening. Okay, so we're gonna, that was our first step. We're gonna fill in this table here with the values for our 4 forces. So we got tension and gravity and normal force, and friction, and finally our net force. So this example has one more force than we did in the last one, but it's essentially doing the same steps to get the answers. So we're going to go through and do the plus minus zeros. So this tension force up here is going right, so that's positive, and it's going up, so that is also positive. For the gravity force, it is only going in the Y, so it's 0 in the X, and it's going in the negative Y because it pulls down. The normal force is only in the Y as well, and it goes up, so that's positive Y. And friction is going left, so that's negative in the X, and it's going to be 0 in the Y. If we think about the sled, it's not flying up or down. It's not like accelerating up or down. So the net force in the Y is 0, like I mentioned at the end of the last problem. This goes to 0 a lot. We're going to add all these columns up to get these boxes here. So we're going to have that boxes, something to fill in later on. Okay, so we're done with drawing our free body diagram and making our X and Y table with the positives and negatives and zeros. So now we're going to kind of try to fill in the two-dimensional one. So this is the tension at the angle theta going across here. So it's going to be 120 at the angle of 25. So let me type that out. So the first one here, to get the tension in the X. So tension in the X would be 120 times the cosine of the 25 degrees. And then for the Y, I'll just type it out now. Ty is going to be 120 sine of 25. We've already filled in the positives or negatives up here, so we don't have to worry about that. So I'm just going to go to the Desmos or calculator and do 120 cosine of 25. and 120 sine of 25. Okay, so it's going to be 108.8 and then 50.7. So we'll just round those up. Some people worry about how much to round. You can stop after 1 decimal or 2 decimals. You don't have to do more than that. So 108, I forgot already, 0.8. Yeah, and then 50.7. So we're done with the tension, 2 components for tension. We're going to find gravity next. So gravity, G equals mg. So we plug in, it says it's 100 is the mass of everything, and 9.8 is the acceleration, so that's going to be 980. So this value going down is much bigger. So this arrow should be much bigger, but it's okay. It's just a sketch. So let me write that in. So 980 is negative. And we're pretty good with that. The only other thing, it says we didn't work with the force of friction is 15. So I can actually write 15 in here. I don't have to do any calculating for that. So I have all the boxes except for this one here. And then I'm going to be missing the normal force box. So this one that I just put a green box around. So those two boxes, if you have all the other spaces filled in your chart, you can do algebra to solve for the other ones. So that's going to be easy enough. So I'm going to solve for the net force in the X, and I'm going to solve for the normal force in the Y direction. So I'm going to add 108.8 and subtract 15. So that's 108.8, and I take away 15. That is 93.8. So this value here is 93.8. Okay. And I have 50.7 going up and 980 going down. I need to know how much this normal force has to go up to actually balance this out. So I'm going to put those two together. So it's 50.7 plus a negative 980. And that's 929.3 going down. But like if it was just those two, that would be the net force going down. So we need the reverse of that going up to get it to go to 0. So we need 929.3 going up. So this number here is going to be 929.3, and it's in the positive direction. So those are all the boxes in the chart. So now I've figured out like my net force, my normal force. I figured out all my forces I filled in the chart. So now it's just using a couple more equations to get these last couple answers. So the coefficient of friction is what this asks for. The coefficient of friction is this symbol U again. So you're going to, or it looks like a cursive U. We're going to use the fun equation or the friction equation to get that. And I'm going to plug in the numbers that I know. So it's 15. You don't have to put in negative 15. 15 is sufficient. U is what we're looking for. And then this 929.3 is the normal force. So again, to get U, you're going to divide 15 by 929.3. That's equal to U. And U is unitless. So it's just the value for it. So it would be 15 divided by 929.3, and it's 0.016, so that's fine. So there is not a lot of friction going on. 0.016, it's a small number. Yep, that's fine. And then go back. So that's that one. That's the coefficient of friction value. And then we're going to solve for the acceleration, where the net force is equal to the mass times the acceleration. And we're going to get that plugging in the numbers that we got here. So it's 93.8 is my net force. My mass was 100, and I'm looking for A. So 93.8 divided by 100 would equal A. Sorry, I gotta move this up so you can see it. And we'll put that in oh, I don't have to put in the calculator, I can do it in my head. It's 0.938 meters per second squared. It's in the positive direction, so it's going right. Okay. So that's it. That's the answer to that one. Hopefully that makes sense with what we're doing. Again, just to summarize, the big ideas are really on this page here. I kind of had it scaffolded for you guys on the worksheet here, but you can always come back to your notes and look at these steps and drawing the free body diagram, figuring out the directions of the forces, filling in that X and Y table with plus minus zeros, get a feel for that. Then you start putting numbers in the boxes. Once you fill in all the numbers except for one missing box, then you can solve for whatever it is. You just use the equations as you need them, the gravity equation, the friction equation. If it's in 2 dimensions, you need the cosine and sine bit. And then you use generally Newton's second law, F equals ma, to solve for the rest. So I will stop there. Hopefully you guys are doing well, and I'll see you next week.